Hello everyone. Today I'm going to talk about magnetic field and forces. Magnetic field and forces. We have learned about electric fields and forces, and we are very clear that stationary charges produces electric field and the corresponding forces on any other test charge. So we have a collection of source charges which are stationary, and that produces electric field. So now we are going to talk about moving charges. The stationary charges cannot produce any magnetic field. We need moving charges. Okay, so we are going to consider a situation where these source charges are moving, and these moving charges produces a magnetic field. Moving charges produces a magnetic field and very similar to electric forces, this can also result into a force. Okay, so we'll try to understand these forces, and this branch of where the magnetic field and forces are discussed is popularly known as magnetostatics. Okay, so the important point here is that we cannot simply borrow the concept of point charge here. We said the charges are moving, but what kind of charges here we are going to discuss? They are not simply the point charges because in magnetism or magnetic fields there are no magnetic monopoles. At least it is not known that magnetic monopoles exist. It does not exist. Magnetic monopoles do not exist. So we cannot simply borrow the concept of point charges from electrostatics. So we have to consider an array of or line of charges. So you will naturally think about currents, okay, the steady currents as a source of charges, okay, that can produce some magnetic field. Okay, so magnetic monopoles do not exist, and we can use steady currents which are flowing through a wire as a source of magnetic field, and this magnetic field will induce some force on some other moving charges. Okay, so this is what we are going to understand today, and we know that, and you have learned previously that you can calculate the magnetic field due to a current carrying wire, using what? Using Biot-Savart law. Current carrying wire by Biot-Savart law. Just like Gauss's law in electrostatics, in magnetostatics we can estimate the magnetic field at any point, okay, at different spatial points, which is given by B of r, it's given by mu 0 by 4 pi integral of IDL cross R hat divided by R square. Okay, and you can see here that this magnetic field is following 1 by R square law, 1 by R inverse square law. It follows inverse square law, very similar to the Coulomb's law. So if you want to compare, electrostatics versus magnetostatics, you can see that Biot-Savart law is what? It is actually the Coulomb's law in electrostatics. Both follows 1 by R square relation. P of R is inversely proportional to the square of the distance. Okay, distance where we want to calculate the magnetic field. So here, let me draw this, what we are discussing. So we want to find the magnetic field at a distance R from a elemental length dl. Okay, and which is part of the magnetic field loop, and this is the direction of current. If you imagine that the current is flowing through a wire, and if you want to find the magnetic field at a distance R, say point P, then this is given by the Biot-Savart law. So that's what I have just mentioned, that P of R is nothing but mu 0 divided by 4 pi integral of IDL cross R hat divided by R square. So now if you want to find the force due to this magnetic field, okay, so we can try to look at the force due to electric field first. Force due to electric field on a test charge Q. We'll try to compare everything from electrostatics because that is what we are very familiar with. So force due to electric field on a test charge Q. Test charge Q is what? Is given by F is equal to capital Q into E, where E is the electric field, strength of the electric field. Similarly, the effect of magnetic field on a test charge is to induce some magnetic force. Okay, and we know that magnetic field curls. So the magnetic force is given by F is equal to Q B cross B. Okay, and this is known as, we'll try to understand this in detail, okay, in a minute. So I'm just giving you this definition, the force, magnetic force. So this is known as the Lorentz force. Okay, Lorentz force. So this, if you see the electrostatic force and the magnetostatic force, in the magnetostatic force there is a cross product involved. We'll come to this cross product anyway. So what is the V? So V here is the velocity of Q, velocity of charge Q in the direction of current, So you might wonder why I have taken this Q, even though I said we cannot simply borrow the definition of point charge in the case of magnetic fields. Okay, So you can, in some cases you will see that this Q represents some elementary charged particles, elementary charged particles. Okay, and you can induce some magnetic force on this charge Q. Okay, and we will see this in the example of cyclotron motion of elementary charged particles, and there is a Lorentz force because of the magnetic field. Okay, so let's try to, so what we are here going to focus here is the charges, collection of charges, moving charges. It could be a line of charge, or it could be a surface charge, or it could be a volume charge, depending upon the kind of charges, charge distributions. We'll try to find the corresponding force, magnetic force. Okay, so let's try to understand this magnetic force, what it means, what is the physical significance, what kind of experiments we can do to observe this magnetic force. So this is what I'm going to discuss. Let's take two wires. Okay, let's take two wires which have currents in the flowing in one configuration. We have current flowing in one direction, and in the other configuration we have currents flowing in the opposite direction. Experimentally, it is found that if you have currents flowing in the same direction, the force is attractive. So these two wires will attract. If you flow a current in the same direction, you can actually make these wires look like the currents are flowing in the same direction. You can also make it flow in the opposite directions, like in this example. So here current is flowing in the second example, the current is flowing in the opposite directions, whereas in the first case the currents are flowing in the same direction. And what is experimentally measured is that force is in the first case, force is attractive. Okay, so these two wires attract to each other, whereas in the second case, where the currents are anti-parallel, the magnetic force is repulsive. Okay, so now how do we understand? So this is very clear to all of you that if we have two current carrying wires which are carrying currents in the same direction, the force is attractive, whereas in the other configuration where the currents are flowing in the opposite direction, the force is repulsive. You can visually see that these wires go away from each other. So what is the reason? So how do we understand? So we know that any current carrying wire, because current carrying wire has moving charges. Okay, mostly it is electrons are moving, but there is an equal number of stationary charges, so that electrically they are neutral. And these moving charges produces a magnetic field. Okay, and just drawing the magnetic field vectors, okay, around the wire. If you place a compass, there should be some reason why I am drawing this. If you place a compass, you can see that the compass is actually curling around the wire. So that means magnetic compass actually represents the direction of the magnetic field. So that is why I am drawing the kind of curl around the wire, so which is actually the the direction of the magnetic field. Okay, direction of the magnetic field. And the current is flowing along the z direction. If I indicate this as z, the current is flowing along this vertical direction, and velocity is also taken to be in the same direction. Velocity of the charges, moving charges, is considered to be in the same direction as that of the current direction. Okay, and here you can clearly see that the velocity charges, and this is in fact a steady current. Okay, so there is a velocity involved here, and this velocity and the magnetic field, they are forming velocity vector and magnetic field vector, forming a cross product, So that means we can have a new vector, which is represented by V cross B. So if this V cross B is acted on another charge Q, then this leads to, because Q is nothing but, you can relate this Q to current, because current is Q by T or dQ by T, etc. So there is a charge in the other wire, and this V cross B will produce a force, which is the Lorentz force, which can be written as F is equal to Q into V cross B. Okay, so we can also now try to find the direction of the force. So from this convention, the right hand rule convention, if I simply draw the directions, the B is along this direction, the tangent, therefore the cross product will be along this direction, so which is the direction of the force. So now you understood the reason for the attractive nature of two parallel currents. So the direction of current is along this way, so this is the direction of velocity, and the magnetic field is this way. Okay, and the cross product is along this direction. So that means the force is directed towards the other wire, therefore this is attractive. Hope you understood this point. So in the other case, if you have anti-parallel currents, the force is going to be repulsive. Okay, force is going to be repulsive. So now we have understood now the force due to electric field and also force due to magnetic field. So now suppose if this charge Q experiences both electric field and magnetic field, what will be the total force? The total force is nothing but Q E plus V cross B. Okay, so this is actually a result of the superposition principle. We can add forces, superposition principle. So also we understood that the magnetic field curls. So now let me ask you, what is the divergence of this magnetic field, because magnetic field has a curl property. So obviously this magnetic field is going to have zero divergence. You will see later this relation, but just for the sake of completeness, that this magnetic field has zero divergence. Okay, magnetic field has a curl property, therefore it has zero divergence. So now we understood about magnetic forces, and we understood that if the same kind of charges experience both electric and magnetic fields, you can write as a sum of both forces, both electric forces and magnetic forces. So now you also know that electric forces do some work. Electric forces do some work. You may ask whether this magnetic forces does any work. Let's try to find out the magnetic forces. Can magnetic forces do some work? Some work. We'll find out in a minute. How do we find the work? The small elemental work done, dW, is equal to the dot product of force and the elemental displacement vector. So this is equal to, we'll substitute for Q due to magnetic field, which is Q into V cross B dot dl, displacement vector. So now this dl can be written in terms of the velocity vector. Okay, Q V cross B dot dl is V into dt, the steady state current we are talking about. So this is, so now dl is nothing but V dt. So now you see this V cross B is, because it's a cross product, is perpendicular to V, which means dW is equal to 0. So there is no work due to magnetic force. Only electric forces can do some work. Okay, so if you want to find some examples for Lorentz force, please look into Griffith 5.1. Griffith 5.1 example for Lorentz force. So magnetic force, cyclotron motion. So there you will see that these elementary charged particles, which is the Q, experience a magnetic force due to the applied magnetic field, and that you can see this motion is balanced by the centripetal force. You please see Griffith 5.1. okay, so now so far we have discussed about the magnetic forces due to some charge. Okay, magnetic force experienced by some test charge Q, because we just borrowed from electrostatics. Okay, but let us be realistic, more realistic. Let's take the typical examples of a line of charges. Okay, a current carrying wire. So how do we express our force in terms of the charge distributions? That's what we are going to, the current distributions, that's what we are going to discuss. So magnetic force due to current distributions, different types of current distributions due to current distributions. So you will encounter different kinds of charge distributions. You will see that there could be line of charges like in the current carrying wire, or you could have surface charge flowing over a surface, or you could have even volume charges, the charge moving across a volume, over a volume. Okay, so now we need to estimate the magnetic force due to these current distributions, to these charge distributions. So what will be the form of the magnetic force? Form of magnetic force. This is what we are interested in. Form of magnetic force. Form of magnetic force. So if, just like the definitions we have used in the electrostatics, the same definitions we will use here also. If lambda is the line charge density, then, and if this charge is moving at velocity v, charge is moving at velocity v, then the current can be expressed as lambda into v. Let's take current as a vector here, because current is actually the direction of the velocity vector, or it is actually the direction which is opposite to the motion of electrons by convention. Okay, so in this case what will be the magnetic force? So we have a line of charges and lambda is a line charge density. So if I simply draw this, so this current carrying wire carries the current, and there is a line charge density which is denoted by lambda, and this is the direction of the velocity, and which is the direction of the current also. And if you take a small interval of length or elemental length, this is nothing but, this can be obtained making it as v into dt. Okay, and we are interested to find the magnetic force and say at point P. So at point P, what is the magnetic force? So magnetic force due to this line charge can be written as F mag, just to ensure that it's a magnetic force or differentiate from electrostatic forces. We just simply write here as F mag. It means it is, the force is related to magnetic field. So this can be written as V cross B into dq, because we have a continuous charge distribution. And what is dq? And this is equal to V cross B, and dq is lambda into dl, because lambda is current density, line current density. Okay, line charge density, lambda is the line charge density. So we can express dq in terms of this line charge density, Okay, so this can be rewritten as v and lambda. We have said before that current is related to the velocity vector through lambda. Okay, so we can rewrite in terms of the current. So this is going to be now v lambda is current vector cross b into dl. Okay, and that is equal to, because current direction and dl direction is same, so we can attribute this direction to one of this. Say we are now talking about we are talking about constant currents in terms of magnitude. Then we can simply rewrite this as I dl cross b and we can even in fact take this I out of the integral, because in many situations, most of the situations, I is a constant in magnitude. It's a constant magnitude, so we can take out of the integral. Therefore we can write this as integral of I into integral of dl cross b. So this is the magnetic force due to a line charge. Okay, so now let's try to find for other kind of charge distributions or current distributions. So here the unit of current is coulomb per second or ampere. Okay, which we are very familiar with it. Unit of current is coulomb per second or amperes. Okay, so now let's try to find. So what we have discussed just now is the magnetic force due to a line of charges or line current. So now let's try to find the expression for the magnetic force due to surface charge distribution. Magnetic force due to surface current density, which I will denote it as some capital K, surface current density capital K. So let's consider a surface something like this, and there is a flow of current. Let's mark it as some, shade it as some red. So this is the elemental length we are considering. So this length is actually, the elemental length is perpendicular to the actual flow of currents. Okay, so this surface current density can be estimated by considering a ribbon. So we have considered ribbon, and the width of the ribbon is dl. So we can also use a perpendicular notation so that it is very clear that this dl is perpendicular to the flow. Okay, and this is in fact two-dimensional. This charge distribution is two-dimensional. So now let's find this K, which is a surface current density. So this is nothing but di divided by the ratio of current to the elemental length perpendicular to the the current distribution. Okay, perpendicular to the flow. So here the current is parallel to the flow. The current is parallel to the flow, or I can say that this is nothing but current per unit width. Current per unit width. Width parallel to the flow, and this current is parallel to the flow, whereas the elemental length is perpendicular to the flow. Okay, so similar to line charge current density, line charge density, for the surface we can write, for the surface we can also write K as equal to sigma into V, just like we have written lambda into V for the line charge density. We can write for the surface current density K in terms of the surface charge density. Sigma is the surface charge density. Surface charge density. So corresponding magnetic force F mag is equal to integral of V cross B into dq. So now dq can be written in terms of the surface charge density, which is equal to V cross B into sigma dA. Sigma dA. Okay, so now this is equal to, and V sigma is K. V sigma is K. So we can simply rewrite this in terms of the surface current density K cross B into dA. Okay, so this expression for the magnetic force due to surface current density. So surface current density is K. So we can express in terms of the surface current density. The charge is actually flowing over a surface. So you will also encounter situations where the flow is over a volume. The charge flow is over a volume. So in that case we can represent the current density as a volume current density J. Okay, so we are trying to find the magnetic force due to this volume current density J, where the charge distribution is over a volume. Volume current density is denoted as J. So let me draw this. How does it look like? So this is the volume, the specimen of wire. Okay, cylindrical shaped wire, and the area of cross section, if you consider small elemental area, if you consider small surface, and this, the J is the current density over this surface, and dA is in fact is a perpendicular, this area of cross section, this small elemental area of cross section is perpendicular to the flow, this infinitesimal cross section area is perpendicular to the flow. So how do we define the volume current density J? Volume current density J is equal to dI divided by dA perpendicular, because this area of cross section is perpendicular to the current flow. Okay, so this is actually, you can also say that this is a current per unit area, and this current is actually along the flow or parallel to the flow, And similarly, we can also express the volume current, volume charge density, or volume current density in terms of the volume charge density. So volume current density, J is equal to rho into V, where rho is the volume charge density, so which is the volume charge density. So then we can express this magnetic force as integral of V cross B into dq, which we always write and substitute for dq in terms of the volume charge density, which is rho into d tau. Okay, d tau is the elemental volume or volume element. Now we can write, and we know that rho into V is J, the volume current density. So J cross B into d tau. So this is the magnetic force due to volume current density. Okay, so now we have written the magnetic force, due to magnetic field in terms of different distributions. So this will be very useful if you want to estimate the magnetic force due to different charge distributions. Okay, so let's try to understand a little bit more on this current distributions, since we have now understood the different distributions, and we can now try to write the current flow across a surface S as current I is equal to, over a surface, J into dA perpendicular. Okay, so we have written J in terms of the current and the area of cross section. So I'm just rearranging. So we can write this current as an integral of J into dA. Okay, so we have simply taken the scalar quantities here without worrying about the directions, but we know that this area of cross section is perpendicular to the flow direction. Okay, so if you want to write in terms of the vectorial notations, we can simply write this as J dot dA. Okay, in terms of the vector representation, we can also write the current. So now let's try to find let's also try to visualize this in terms of the actual flow of charges. Okay, in terms of the actual conservation of charges. So if you consider this charge over a volume V, so what is the total charge per unit time leaving a volume V? So total charge per unit time leaving a volume V. So this is total charge per unit time is nothing but over a volume V is J dot dA over the surface S. Okay, that is equal to, using divergence theorem, you can also write this as over the volume as the divergence of this current density, okay, over the volume element ditto. So I have used the divergence theorem because I can convert the surface integral into a volume integral. So now since charge is conserved, you know that charge is conserved, charge cannot be created, charge is conserved, we can simply write this expression del dot J into d tau as the change in the density. Okay, d rho dou rho by dou t over this volume into the volume element. Okay, so see the divergence of this current. So the current charge per unit time, total charge per unit time leaving a volume V is equal to the change of that charge. Okay, the negative sign is because the charge is decreasing because it is flowing. Negative sign because there's a decrease in charge due to flow. Okay, this means I can simply rewrite this as del dot J plus dou rho by dou t into d tau, that's equal to 0 for a finite elemental volume. I mean, volume element has to be finite. The only possibility is that del dot J plus del dot J is equal to minus dou rho by dou t, which is known as the continuity equation. Okay, continuity equation, which is related to the flow of charges. Flow of charges. Okay, so what we are considering here is the steady state currents. So steady state currents means dou rho by dou t is equal to, there is no change in the charge density. That means there is no pileup of charges over the surface, over the volume. There is no pileup of charges. There is a steady current. So in that condition, under this condition, del dot J is equal to 0. So what we are discussing here is the magnetic field due to steady currents. Okay, we are not talking about the changes or the dynamics of the system. We are only considering the steady state situations. Okay, this is very important, and that is where this magnetostatics is all about. Okay, you will see that later that we also will deal situations where this is also valid. There is actually a change of charge. There is a dynamics involved. And we will see the corresponding changes. Okay. So what is the meaning of this statement? Del dot J is equal to 0 means there are no sources or sinks. Okay, there are no pileup charges, there are no sources, there are no sinks. So we only have steady state currents, and these steady currents produces magnetic fields. Okay, this steady currents produces magnetic field. Steady currents diffuse magnetic field. Okay, so now since we understood the different kinds of current distributions, we can also write the Biot-Savart law. The Biot-Savart law in all these current forms, okay, distribution forms. Biot-Savart law with surface, we have already written in terms of the line charges. We can write in terms of the surface and volume current densities. Okay, so usual form is, which we have already written, B of R. B of R is mu 0 by 4 pi integral of I cross R. So let me take the separation vector, square of separation vector into a prime elemental length, and here mu 0 is 4 pi into minus 7 Newton per ampere square, so that you get the right unit for magnetic field. Okay, like Tesla is the unit of magnetic field. So in terms of the surface current density K, we have the surface current density K, surface current density K. Let's write the Biot-Savart law. Biot-Savart law in terms of surface current density. Surface current density K look like this: mu 0 divided by 4 pi K R prime. Okay, so we are interested to find the magnetic field due to a current density, surface current density K of R prime cross our separation vector R cap R square into, now we have to consider the area element because we are interested to find the magnetic field due to surface current density. Similarly, in terms of volume current density J, volume current density J, we can also write the magnetic field B of R is equal to mu 0 divided by 4 pi J of R prime cross separation vector R hat divided by R square into d tau prime. Okay, so we have expressed the magnetic fields, the Biot-Savart law, in terms of the various current distributions. Okay, so now let's try to find the divergence and curl of this magnetic field. Let's try to find we already know that magnetic field has the curl nature and its divergence is going to be 0. Let's try to understand this better. So we are going to now find the divergence and the curl. Okay, curl of magnetic field, because we already learned about the magnetic forces, different magnetic forces. Okay, magnetic forces due to different distributions. Now we are trying to find the divergence and curl. Okay, how can we relate? Since we know magnetic field, we can also try to find, we can take the divergence of this magnetic field and curl also. Okay, and this magnetic field has a curl nature, so it's also known as pseudo vector. Okay, magnetic field is also known as a pseudo vector because it has the curl nature. So So this is the current carrying wire, and we know that magnetic field is curling around the wire, around the current carrying wire. So if you consider a loop, let's consider a loop with a radius of s, with a radius of s for the loop, and this current carrying wire generates a magnetic field around the current carrying wire, and this denotes the magnetic field around the current carrying wire. And if you take a closed loop line integral of this magnetic field B dot dl, and in fact we can find the magnetic field for this configuration using the Biot-Savart law, which we will try in the interaction session. So let me write down the value of the magnetic field which you are going to get for this radius s, which is actually mu 0 I divided by 2 pi s. Let's only take the scalar quantities, okay, because it has to be in the same direction anyway. Magnetic field has to be in the same direction as that of the elemental length, okay. And if you find using Savart law, we'll see that magnetic field is mu 0 I divided by 2 pi s, okay. And this one is, because these are all constants, you can take out of the integral mu 0 I divided by 2 pi s integral, closed integral of dl, which is actually the perimeter of the circle, so which is equal to 2 pi s. So therefore this is going to be mu 0 I, okay. And interestingly, this is independent of radius, independent of s, independent of s. So this is interesting because the magnetic field, if you have a larger s, the magnetic field is going to be smaller, so the product always remains the same, okay. So now, here we have just talked about one kind of wire, okay, one current carrying wire. Now if you imagine that the whole closed loop has several of these current carrying wires. If you take a closed loop, imagine that you have, suppose if I take this closed loop and I have several of current carrying wires, okay, several of current carrying wires, even some can be outside of this closed loop. So then this integral, closed integral, can be written as P dot dl is equal to mu 0 I enclosed, where I enclosed is the current inside the integration path, okay. So I enclosed is the current inside the integration path. So now let's try to write this in terms of the current density. We know how to write I enclosed in terms of the current density. I enclosed is equal to integral of j dot dA, okay, j dot dA. So now I can substitute and rewrite this B dot dl is equal to mu 0 into j dot dA, okay. So now I can convert this line integral into a surface integral using Stokes theorem. So let me write this line integral B dot dl in terms of the curl of the magnetic field. So this is a result of Stokes theorem. We can convert line integrals into surface integrals. So this is equal to mu 0 into j dot integral of j dot dA. Okay, so now if I simply, so this is also surface integral, so I can simply take this to the left hand side, minus mu 0 j dot dA, that's equal to 0. So now for a finite elemental area, del cross B should be equal to mu 0 j. Okay, so this is the differential form of Ampere's law. Form of Ampere's law. The integral form is the one we have already written. B dot dl is equal to mu 0 into I enclosed. Okay, so this is the integral form of the Ampere's law. And this one is the differential form of the Ampere's law. Okay, so we can use this expression Ampere's law to find the magnetic field for a current carrying wire. So for simple symmetries, this is going to be very useful. You can estimate the magnetic field without going into Biot-Savart law. You can simply estimate the magnetic field if you have a simple symmetry like current carrying wire. Okay.